Deep within the heart of mountains, massive machines slice through rock, clashing technology against nature. And through these clashes, the wonders of the modern world are born.
Deep beneath China's mountain ranges, a quiet industrial revolution has been unfolding. While highways and rail lines curve gracefully across the surface, another network is being carved straight through solid rock. Tunnels stretching for tens of kilometers, completed in timeframes that have stunned engineers around the world. These are not symbolic megaprojects. They are infrastructure on a scale that reshapes geography itself. China now operates some of the longest mountain tunnels ever built, including projects exceeding 22,000 meters in length. What makes this remarkable is not just their size, but the speed, consistency, and safety with which they are constructed. To understand how this is possible, it is necessary to look beyond the machines and examine the system that surrounds them. The decision to tunnel through mountains rather than around them is not driven by spectacle. It is strategic. Mountain roads are slow, dangerous, and expensive to maintain. They wind upward in sharp turns, are vulnerable to landslides, and become choke points during severe weather. Tunnels eliminate those variables. They shorten travel times from hours to minutes, stabilize logistics routes, and create predictable corridors for economic activity. In China's planning model, that predictability is everything. The process begins long before any excavation. Route selection is treated as a scientific problem rather than a political one. Engineers analyze geological maps, seismic histories, fault lines, rock density, and groundwater behavior. Boreholes are drilled across multiple candidate routes. Ground-penetrating radar is used to identify voids, aquifers, and unstable zones that could derail construction later. Only after repeated rounds of testing does a route survive. Once a tunnel is approved, planning shifts to industrial coordination. Unlike many countries that outsource components globally, China relies almost entirely on domestic manufacturing. Tunnel linings, concrete segments, ventilation ducts, and support systems are prefabricated in factories months in advance. This approach minimizes delays once excavation begins. When the rock is opened, the tunnel is already waiting to be reinforced. At the center of most projects is the tunnel boring machine, or TBM. These machines are not generic tools. Each one is custom designed for a specific tunnel. Rock hardness, depth, pressure, curvature, and groundwater conditions determine everything from cutter head geometry to motor torque. Some of China's largest TBMs weigh more than 5,000 tons and stretch longer than a football field. China does not import these machines. It builds them. State-owned manufacturers now dominate the global TBM market, supplying equipment not only domestically but to major projects worldwide. Before a single component is assembled, engineers construct full digital twins of the machine and simulate months of operation under predicted conditions. Only after repeated testing does physical assembly begin. Transporting a TBM to a mountain site is itself an operation. Machines are disassembled into massive sections, hauled by specialized vehicles, and reassembled inside a vertical launch shaft. This shaft is not an afterthought. It is a precisely engineered cavity designed to anchor the machine safely and prevent collapse when excavation begins. Only then does the mountain start to move. The TBM's rotating cutter head grinds forward, pulverizing rock while hydraulic systems push the machine ahead with enormous force. As it advances, mechanical arms install prefabricated concrete lining segments behind it, forming a permanent tunnel wall in real time. These segments do more than reinforce the tunnel. They also serve as anchor points, allowing the TBM to brace itself and continue pushing forward without relying on unstable natural rock. Excavated material is mixed with water to form slurry, which is pumped back to the surface. There, recycling plants separate rock and sediment before returning the water to the system. This closed-loop process reduces environmental impact and ensures uninterrupted operation deep underground. Throughout excavation, the machine is constantly monitored. Sensors track gas levels, seismic vibrations, ground deformation, and oxygen content. Ground-penetrating radar scans ahead of the cutter head, giving engineers early warning of faults or cavities. If conditions change, the TBM can be slowed, reconfigured, or stopped before a failure occurs. This level of monitoring is one reason TBM tunneling is now considered the safest method available. Still, TBMs are not always suitable. In zones where rock composition changes rapidly, where tunnels must curve sharply, or where geological conditions are too complex, China relies on alternative methods. Controlled drilling and blasting remains in use, though far less frequently than in the past. This method demands extreme precision. Explosive charges are placed deep into drilled holes, timed carefully to fracture rock without destabilizing surrounding structures. After each blast, ventilation systems clear dust within minutes, and engineers assess structural integrity before any worker enters the area. Because of the risks involved, blasting is being steadily phased out in favor of sequential excavation. Sequential excavation divides the tunnel face into sections, removing and supporting them in stages. As each segment is excavated, supports are installed immediately. Sprayed concrete, steel ribs, and rock bolts that stabilize the ground before it can shift. This method allows the surrounding rock to settle gradually into a stable configuration rather than collapsing suddenly. Sensors embedded throughout the tunnel monitor deformation in real time. If movement exceeds thresholds, additional support is added instantly. The tunnel is not forced into shape. It is guided into equilibrium. Once excavation reaches its endpoint, the TBM breaks through into a reception shaft. Depending on the project, the machine is either disassembled for reuse or permanently buried beneath the landscape. In many cases, roads or rail lines are later built directly above the entombed machine, sealing it as part of the structure it helped create. Post-construction work continues long after the digging ends. Waterproof linings are installed, fireproofing systems are added, ventilation, lighting, and monitoring networks are integrated. Even after opening, tunnels are continuously observed for leakage, stress, or deformation, ensuring decades of safe operation. What distinguishes China's approach is not a single innovation, but integration. Planning, manufacturing, excavation, and monitoring function as a unified pipeline. Delays in one area do not cascade into failure elsewhere. The result is speed without improvisation and scale without chaos. China's longest mountain tunnels are not monuments. They are tools designed to compress distance, stabilize trade, and bind regions together through infrastructure that operates out of sight. The mountains above them remain unchanged to the casual observer. Beneath them, however, a vast engineered world continues to grow, measured not in spectacle, but in kilometers of precision-cut stone.